metals. When you look at the periodic table, you'll notice that the majority of elements are metals, and these are all the ones in the yellow. The ones in the grey over here on the right hand side are the non-metals, and don't forget hydrogen over in group 1 is also a non-metal. And on the staircase here, separating the metals and the non-metals, we have the metalloids. Most metals are found in nature combined with other elements, and these are called ores. And you'll have seen iron ore before. It looks like this reddy colour. It's a mixture of different iron compounds, and also other elements are in there as well. And bauxite is the other name for aluminium ore, and it looks quite cool. It's speckled like this. Metal is extracted as its pure form from these ores via different processes. Properties of metals. Metals are lustrous. You can see here that it's nice and shiny, and lustrous means that it reflects light. They are opaque, which means light can't pass through this. You also can't see through it because of that. They're good conductors of electricity, and they're good conductors of heat. And that's why we use them for cooking. They're also malleable, which means that they can be forcibly bent or hammered into shape. And you can see here someone's bending it. Sometimes it requires a little bit more hard work, but they can be reshaped using force. And they're ductile. And by ductile, we're talking about the ability to be drawn out into a wire. Most metals also have the following properties: that they're hard, that they've got good tensile strength, and by tensile strength we're talking about the ability to be able to withstand a pulling force. They've got high melting and boiling points, and they've got a high density. Now, as I said, most metals have those following properties. Straight away you can think of mercury, which doesn't follow any of these because it's a liquid at room temperature, so it's got a low melting point, low boiling point. It's not hard, it doesn't have the high tensile strength nor the high density. But most metals will have these properties as well. So what I want to do now is have a look at the structure of metals and metallic bonding, and this is going to explain the properties that we've just spoken about. So when we think about a metal atom, it will have a small number of valence electrons, so anything from 1, 2 or 3 electrons in its outside shell. And it's also got low electronegativity. In other words, these electrons here are easily removed from the atom. It wants to get rid of those electrons. So what happens is that these electrons are all shared between all of the metal atoms. So you get a structure which is a metal cation. So here you've got the zinc 2 positive, which is then surrounded by a sea of delocalized electrons. These electrons are delocalized from the atom or from the cation. So the atom releases the electron into this sea, and it shares these electrons, and this sea of delocalized electrons is what gives metals their characteristics and their bonding. So it looks something like this. This is a version of it moving, because remember, everything's got kinetic energy, so these particles or the cations will be vibrating and the electrons will be whizzing around in between. These metal cations are arranged in an organised and closely packed lattice. So you can see here it's sometimes represented just with the cation in the middle and as the sea of delocalized electrons around the outside. It's represented here as a cloud of valence electrons because, as we've already learned, if I look back at the previous slide here, electrons are whizzing around so fast that they form a cloud effect, and that's Schrodinger's waves or cloud effect. So we know about the structure how does that structure give it the properties that metals have? Let's look at the high melting and boiling point. Here we have our positive cations and our sea of delocalized electrons. There is a very strong electrostatic attraction between positive and negative. So we've got strong electrostatic attraction between the delocalized electrons and the metal cations. And what this creates is, it's almost like glue. This cation's attracted to the electrons in between, which those electrons are attracted to the cation. So it's a strong electrostatic attraction. And this means that metallic bond is a very strong bond. They conduct electricity. And the reason for that is because of the sea of delocalized electrons. For something to conduct electricity, there must be some form of free moving charge. In this case, we've got the electrons are able to move. So what happens when we apply a charge is the electrons will move from the negative terminal here, and they'll go in the direction of the positive terminal. They're attracted to the positive side. With this free moving charge, metals are able to conduct electricity. They're good conductors of heat. And here what happens is if we apply some heat energy, the electrons will bump into the cations and also bump into the other electrons and can transfer that energy across. So the delocalized electrons are able to carry that energy and bump into other metal ions, and this just transfers the energy, because remember that heat is just energy. So you'll see here, if one of these gets energy, it will move faster, and it will move then on to giving some of that energy to the next cation or to the next electron and make that one move faster. Metals are malleable and ductile, and again we can explain this with the sea of delocalized electrons. They are able to rearrange themselves to hold the cations together. So what happens if I apply force to this lattice, which again I've just got my cations which are arranged in a closely packed lattice with my sea of delocalized electrons around the outside. If I apply a force to this lattice, what will happen is these cations are just pushed across, but the electrons just rearrange themselves around the outside, so it becomes quite stable. This means that you're able to bend it, and it also means that it's ductile. And this is exactly what happens if you stretch out a metal. Those electrons will just move around the outside of the cations and rearrange themselves so that there's still the positive with the negative in between. So the sea of delocalized electrons just moves around and still holds the cations together. And they are lustrous, and the reason that they're lustrous is that the free electrons in the lattice can reflect light. And you can see here the light bounces off, hits the free electrons and is reflected, and that's what causes reflection. They're also dense, and we've already pretty much discussed this. It's because of the electrostatic attraction between the cation and the delocalized electrons. Group 1 metals are softer and they have lower melting temperatures. The reason for this is if you look at how many electrons are donated into the sea of delocalized electrons by group 1 metals. Group 1 metals will offer up 1 electron into the sea of delocalized electrons to give a cation with a positive 1 charge. A group 2 metal, on the other hand, offers up 2 electrons into the sea of delocalized electrons to leave it with a 2+ charge on its cation. This 2+ charge is a stronger positive charge, so it will be more strongly attracted to the electrons than the positive one charge will to the electrons. So it makes sense that these have a higher melting temperature because they're held together with stronger forces. Group 1 metals will be softer because they're more flexible, because there's less of this electrostatic attraction occurring again. So you should now be able to answer these chapter 5 questions.